There are measures of phonation that attempt to more directly visualize the position of the vocal folds or the opening of the glottis. These include electroglottography, which is focused on the size of the opening of the glottis, endoscopy, which is use of a video camera to visually inspect the larynx and the function of the vocal folds in video, and videokymography, which uses an endoscopic image to measure glottal opening. In electroglottography, an electrical signal is generated that relates to glottal opening. The client wears a band around their neck that has 2 electrodes on it. A low voltage electric current travels from one electrode to the other, including across the vocal folds. Recording how much conductance of electrical signal reflects the degree of glottal opening. Less current travels when the vocal folds are open because electricity doesn't travel across air very well, and more current travels when the vocal folds are closed. We can then graph this conductance as a waveform, and that's referred to as the laryngeal wave, and it has a characteristic look. Here are a couple of different examples of linguistic waveforms. In the upper left, we have a smoothed out version of a waveform that you would get from recording an actual production. This is in the textbook. It has one small error in it, though, in the point at which the inferior margins of the vocal fold make contact with each other as part of the closing phase. A line drawing a schematic of that linguistic wave is shown in the lower left, where the different elbow points reflect different properties of the vocal folds coming together across the cycle. And again, since this is the amount of electricity that is conducted, when the curve is near the bottom and the conductance is low, there's relatively little contact, so that means open. And when the current is high up near the top at the peaks, that is when the vocal folds are closed. And you can see this in the part of this image on the right, which more directly relates a cross-section looking at the vocal folds and their contact with each other, along with where you are on this linguistic wave. So when things are very open, such as kind of in the middle of this image, the values are very low. And when things are very closed at the beginning or at the end of the cycle, the values are very high. In electroglottography, different registers of phonation are reflected in different phonation waves of the larynx. So in the upper right here, we have the kind of wave we've been looking at for modal phonation. In a falsetto voice, which is very high-pitched, you have a much more frequent cycling of the vocal folds. In a pulse voice, which has a lower and more irregular frequency, you may see multiple different peaks, or as in here, kind of a bimodal pattern where it goes from a kind of bigger regular looking wave to a smaller fluctuation wave. With a very breathy voice, we have a large open phase, and since the voltage is low when the vocal folds are open, we have more time spent near the bottom on the linguistic wave. And then the final example here is a very irregular looking wave, which you might see when you're dealing with a hoarse sounding voice, for example. Various measures can tell us about the movement of the vocal folds and the opening of the glottis in the laryngeal wave. The closed quotient is a commonly used measure which looks at the duration of the closed phase, so how much of the cycle is quote-unquote closed. Given that this wave is a kind of a continuous thing, you have to pick a point that you're going to call closed versus open. In the graph at the right there, that would be at that line indicated by HC, about halfway up the wave. The open quotient is just like the closed quotient, but it focuses on the open part instead. So in either case, it's a percentage of the duration, basically, that is spent either closed or open. So if you add the two of those together, you should come up with a total of 1 or 100%. There are a couple of other measures that look at ratios of different durations. So for the contact index, you take the closed duration and subtract the open duration and then divide that by the closed duration. So if the closed and open durations are pretty close to each other, that will be near 0. If the closed duration is long, then that will be positive, and if the open duration is long, then that will be negative. The closed to open ratio just looks at the ratio of those two durations to one another, so relatively balanced would be near 1, where closed and open are about the same. If the number is large, it's more closed than open, and if the number is a fraction, small, less than 1, it's more open than closed. The speed quotient is basically the same thing, but it's open duration over closed duration instead. For all of these various measures one could take from the linguistic wave, we would again have norms for typical productions by males and females at different ages that we could compare these ratios to. In looking at closed quotient, for example, a modal voice has a closed quotient between 0.25 and 0.65. As we increase the loudness of the voice, the closed quotient increases, so we hold the vocal folds together harder and cause more air pressure to be required to blow them apart. Pressed voice has a generally higher closed quotient. The vocal folds spend a lot of their time closed during the cycle. A breathy voice has a lower closed quotient because the vocal folds spend more time apart, or may even be mostly apart throughout the entire cycle. A falsetto voice has a slightly lower closed quotient than a typical modal voice, reflecting a slightly different means of vibration happening in falsetto. What you might think of as a more direct visualization method for the larynx uses endoscopy, a small camera that you can fit inside the vocal tract to look at the vocal folds. In a rigid endoscopy, there's basically a small camera at the end of a stick that you can put in the oral cavity. If you then have somebody phonate a high front vowel like E, that moves a lot of the tongue root out of the way and allows you to see what the larynx is doing. In a flexible endoscopy, a fiber optic camera is threaded through the nasal cavity to hang down through the velopharyngeal port. You can look at any kind of speech you want to with a flexible endoscopy because that location of the camera is relatively out of the way of speech production. Regardless of what type of endoscopy, rigid or flexible, you're using, phonation is generally too rapid to be visualized by video, and so we have to do something special. One means of getting a view of phonation with just an ordinary video camera is to use a process called stroboscopy. In stroboscopy, a computer monitors the fundamental frequency of the speech. So generally you can only do this when you have smooth phonation, when you're having somebody phonate just a plain old vowel like an E or an Ah. A light source flashes at a speed that's slightly slower than the fundamental frequency of the voice, and this causes the phonation to be imaged at slightly different points within the cycle. So for example, what's shown here would be, at point A when there's peak closure, if that was a glottal larynx waveform, we would take one picture, and then in point B of the next cycle where things are slightly heading toward opening up, we would take another picture. At point C in the next cycle where things are opening up even a little more, we would take another picture. At point D where there's probably some actual visible opening from the top down of the larynx, we would take another picture. In the next cycle at point E, we would take another picture when things are even more open. And then in the last cycle shown here at point F, near to the peak opening of the vocal folds, we would take another picture. So by compositing all of these pictures together, we get something that looks kind of like a slow motion video of phonation, even though it's being taken from phonation in real time. The alternative we have for that, and this may be more common as technology gets better and better, is to have a high-speed camera that can image things at a much higher rate. A standard camera uses about 30 frames per second, or an imaging rate of 30 hertz. When we look at phonation in stroboscopy or high-speed video, there are a variety of parts of the larynx that we take a look at. The edge of the vocal fold in the middle should be relatively smooth and straight. There should be complete closure of the glottis along the length of the vocal fold during the closed part of the cycle. We can look at how much the vocal folds open during a phonation in their opening phase. If that opening is either unusually tiny or unusually large, that may indicate at least a deviation from modal phonation, if not some other phonation problem. We can look at the symmetry of the opening and closing phases in phonation. In typical phonation, that's relatively balanced, but it may be unbalanced in abnormal phonation. There is something called the mucosal wave that one can look at in phonation, where as the vocal folds open, you can see sort of a small ripple across the top of the vocal fold, and that ripple goes about halfway along the width of the vocal fold before it dies out. As you engage or disengage phonation, we can look at the symmetry and movement of the left vocal fold or the right vocal fold to look for muscular weakness or paralysis. And then also we can look at what's happening above the glottis. So for example, if the false vocal folds are obscuring the true vocal folds, there's too much compression going on. We can also look to see whether the larynx looks relatively round or whether it seems compressed anterior to posterior. All of these would give us indications of abnormal muscular activity being involved in phonation. So here, for example, we have a couple of still pictures of the larynx during the glottal cycle. The vocal folds and the glottis are quite open in the image on the right, and things are almost completely closed off in the image on the left. Looking at the vocal fold edge, it seems relatively straight and even. It may be a little hard to tell in the vocal fold that's on the right side of the image, which would be the left side of the person in the opening phase, but I think that's a little bit of shadow rather than an actual wobble in the shape of the vocal fold. Where the vocal folds are closed, there's still a little bit of opening left over, and it could be there's some irregularity in the vocal fold that maintains that open space. Since we don't have a moving image here of the vocal folds, we can't look at things like phase closure or the mucosal wave or phase symmetry. In terms of supraglottic activity, the vocal folds seem, relatively lengthened, and we can clearly see the vocal folds themselves beyond the false vocal fold, so there doesn't appear to be excess compression happening. Our last visualization method would take a video image of vocal fold vibration from laryngoscopy and would look at a cross section of that image, and a computer would basically automatically detect the black in the middle of that image, and you can turn that into a picture or a video where you look at just that cross section as it varies over time, and that gives you something like the picture you can see at the far right, which is called a kymographic image of vocal fold vibration. So you can look at whether the vocal folds completely close, which they don't in this particular image. You can also look at left and right asymmetry to see whether the picture looks relatively balanced in the wave on the left side and the right side. And it's possible to make a kymographic image more easily than it is to make a full video image at the speed of vocal fold vibration, because you can just be tracking that one cross section of pixels in the video image instead of the full 2-by or 2-dimensional field of pixels across the full video.